Bueno, él hizo el doctorado en el Instituto de Física de Lebedev en Moscú y su tesis de doctorado se titula Dynamics of Dark Matter in Galactic Centers. Él es especialista en dinámica de galaxias y particularmente es un expertazo en simulaciones numéricas. Entonces, sin más, ya presentamos al doctor Vasiliev. Adelante.
Thank you. And they just disappeared. Okay. Thank you for inviting me to give a talk here. I'm actually not going to talk that much about n-body simulations. I will just present a broad brush picture of the evolution of binary supermassive black holes, which is nicely summarized in this cartoon. In general, the evolution of binary supermassive black holes does not occur in the empty space. They are embedded in galaxy. Galaxy has stars, and that's the interaction between the binary and the stars, which actually is at the core of the evolution, which is depicted here. Basically, these black holes, they have to do something nasty with the stars in order to evolve. I will present both theoretical and a bit of observational introduction to the subject. We'll talk just a little bit about my own work, but in general it would be more at the introductory level. So I will start with a theoretical description of how do we expect the binary supermassive black holes to form and evolve, and what are the potential bottlenecks in this process, and so on. And towards the end of the talk, I will present a few observational pieces of evidence about the binary supermassive black holes. So why do we think that the binary supermassive black holes should exist in nature? In principle, because in the standard cosmological scenario, galaxies merge, and they do it quite vigorously. Sometimes a galaxy can have many dozens of mergers per Hubble time, or at least a few mergers. And if you think that many galaxies do host supermassive black holes at their centers, it is quite natural that each such merger eventually creates a binary supermassive black hole. Maybe it would not be that obvious from the outset, but I will try to convince you that this is the case. Consequently, these binaries, they form and then they evolve themselves. And eventually, we expect that most of the black holes which form a binary, they eventually merge themselves or coalesce, emitting gravitational waves, which potentially could be detectable. And so the theoretical description of this process must take into account the formation of the binary and its subsequent evolution. And the very basic question that we may ask is how often do we expect these binaries to form, and how long do they live before coalescing, and so on. So an evolutionary track of a typical binary supermassive black hole can be split into several stages. First, a merger of two galaxies, it creates a common core, a common galaxy remnant. And the black holes, as they are heavy objects, they sit in the center of each individual galaxy. And when the galaxies merge, they also sink towards the common center because of dynamical friction. And this process brings them together, because if they're far apart, we cannot talk about the binary. They are just two separate black holes. But if they come closer, so that they feel mutual interaction more strongly than the force from the rest of the galaxy, that's the moment that we can talk about a binary as opposed to just two separate black holes. So at the very beginning, when the binary has just formed, it experiences a very rapid period of strong interaction with the field stars, which I'll come to just slightly later. So the initial stage is very rapid, and it leads to a creation of a core in a galactic center, for the reason, again, that I explained slightly later. But then the evolution slows down considerably. So the most part of the time the binary spends at the radius of separation between the two components is a sub-parsec scale. And it eventually decreases, and when it decreases to roughly 10 to minus 2 parsec, then it's not just a single moment that something turns on. The thing is that gravitational wave emission is very strongly dependent on the separation between the components. So when they get closer, the emission of gravitational waves becomes stronger and stronger. And roughly 10 to minus 2 parsec is the threshold for the time scale for gravitational wave emission to become shorter than the Hubble time. So it accelerates and then eventually merges very rapidly. So graphically, it could be depicted as follows. So we have the initial stage of the galaxy merger when the two black holes are still far apart, like many kiloparsec away, and they sink towards the common center due to dynamical friction. But then this early stage is very rapid, so you see that during this early stage it can shrink by a factor of even 1,000 or so. Basically, the binary forms when the separation between the two components reaches the radius of influence of the black hole. And the radius of influence itself is defined as the radius containing the mass of stars equal to twice the mass of the black hole itself. So in other words, the radius within which the black hole dominates the gravitational potential. So when it forms, then it rapidly sinks towards, it rapidly shrinks by a factor of at least 10 or even more. And then the binary becomes harder and harder. In stellar dynamics, hard means that the orbital velocity of the binary is greater than the velocity dispersion of the field stars. So when the binary becomes hard, then its evolution slows down. And this is driven by the so-called loss cone processes, which I will describe again later. And then, as you see, when it reaches the threshold of gravitational wave emission, then it starts to accelerate once again, and then eventually it, boom, goes towards the merger in just a fraction of a second. Well, maybe not a second, but in a very short time. Why does the binary shrink in the first place? Because there are three-body interactions with the field stars. So it's not sitting in a vacuum. There are stars around it in the galaxy. And when a star comes into the vicinity of a binary, it experiences a very complex interaction. So this is the binary, and the star, you see, it first arrives at some sort of elliptic orbit, but this is, of course, not a Kepler orbit because it's not in just a single point mass in the center. There is a time-dependent potential which perturbs the orbit. So then it is engaged in a very complex interaction, but eventually this interaction ends when the star is ejected back, and it is ejected with a velocity higher than the velocity of with which it was coming in. So the star extracts energy and angular momentum from the binary, and conversely, the binary shrinks little by little. So this process, if we embed the binary in the bath or a thermal background of stars with the given density and velocity dispersion, then we can derive the rate of hardening, which is the rate of change of inverse semi-major axis. This is the binding energy of the binary. And it would stay constant with time, so it would keep shrinking until the emission of gravitational waves becomes important. But the truth is that, of course, if we eject all the stars which come in, eventually we run out of stars. So the binary, this is the reason why initial evolution was very rapid, but then it slows down considerably because binary runs out of stars which were immediately available, the reservoir of stars with low angular momentum, which can come close to galactic center. And then the subsequent evolution is driven by the rate at which these stars are replenished. But before I come to that, I will describe another effect which might have some observational consequences, namely the depletion of cusp and formation of galactic cores. So once again, when the two galaxies containing black holes merge, they originally might have had a cusp density profile each. But then, when the binary forms here, this is this sequence of snapshots from an n-body simulation. And you see, when the binary forms, then these contours show the equidensity surface. So when the contours become sparser and sparser, that, of course, means that the density drops precisely because of this effect, because it ejects stars from the galactic nucleus. So the density of stars here decreases considerably. This is still a binary, even though you cannot distinguish because it's very close. But these are still two black holes, not just one point. And this process can lead to what people call depleted cores. So if observationally, we know that most galaxies somehow are well described by a searching density profile. But then people, if they look at some galaxies, they see that if they extrapolate this density profile towards the center, they see that the actual density profile is a bit below this extrapolated value. So that has been interpreted as a signature of the core depletion. I would warn against a very direct interpretation of this result because, of course, we do not know what there is no fundamental physical mechanism why all galaxies must follow a Sérsic profile. So any sort of extrapolation is a bit of uncertain. But the thing is that indeed if there is a clearly defined core, and moreover, if there is also a kinematic signature in the very center of the galaxy in form of a tangential velocity dispersion, then it could be taken as a hint that previously in this galaxy a binary supermassive black hole might have existed. Now, we are done with the first part of the evolution, very rapid evolution, and then, as I told you, the evolution slows down considerably, because now it is limited by the supply of stars which can interact with the two black holes. This process has quite a lot in common with a similar theory for single black holes and for tidal disruption rates of stars around single black holes. Basically, you need to throw a star on a very radial orbit so that it can approach the black hole and get tidally disrupted or just plunged into the black hole. The same thing is true for a binary, but in this case, the cross-section of this process is not just the radius of the black hole, but it's the radius of the binary. As we have seen, the star must approach to within 1 or 2 separation between the black holes in order to engage in this complex interaction. So this is the semi-major axis of the binary, the separation between the two components, and the angular momentum of a star must get below this value. But of course, if we run out of the stars which had this angular momentum below the threshold, then we have to replenish it somehow. One process that is always acting is the two-body relaxation, which shuffles constantly the angular momentum of stars in the galaxy. But we know that the galaxies have very large number of stars, so the two-body relaxation times in galaxies are very long, considerably longer than the age of the universe. On the other hand, we see that what we need here is the time scale for not for relaxing entirely. Two-body relaxation time scale is the time needed for the angular momentum to change by order of itself. But here, it only needs to be changed by a small amount. So basically, a star which was just outside the lost cone, which had the angular momentum small enough, but not small enough in order to get into the lost cone, it just needs to change the angular momentum slightly. So there is a small factor here in front of the relaxation time, and this is the time scale for repopulating the lost cone. But still, even that time scale is much longer typically than the orbital period. So every time a star acquires angular momentum below the threshold, it gets eliminated, it involves in this interaction with the binary within one orbital period and then gets ejected. So on average, there are very few stars. The lost cone is almost empty. And early estimates of the efficiency of this process led to the very grim conclusion that the binary would just stall, it would not evolve anymore. And this has been dubbed the final parsec problem, because the typical separation between the components is about 1 parsec. And I remind you that there was a, just once again, once again, to this plot, this is the span of radii that we need to bridge from the formation of the hard binary. Basically, it needs to shrink by 1 or 2 orders of magnitude in order to reach this regime. So this is this 1 parsec you see here. This is 1 parsec. Roughly, that's where you would expect the binary to stall. But of course, this conclusion was based on a very idealized scenario that the galaxy is entirely spherically symmetric, which of course is not the case, because the merger remnants, there is no reason why they would be spherically symmetric. They would be flattened, they might have some rotation, they might have some perturbations like residual perturbations, ring down of these large scale asymmetries. And what happens in non-spherical potential is, of course, the angular momentum is not conserved. So before we were talking about stars that need to go to get to very low values of angular momentum, but now if you compute the orbits of stars in a typical non-spherical potential and track the evolution of angular momentum, you see that it oscillates back and forth. This is for the precisely axisymmetric case. This is for a case which is not even axisymmetric, which is triaxial. And you see that in principle, even if star initially had an angular momentum way above the threshold, way above the lost cone boundary, then eventually it can get below this value in a in a time scale of, say, a few orbital periods. And that happens without any two-body relaxation. So even if two-body relaxation is not effective in galaxies, we still expect that this mechanism may drive stars into the lost cone from a much larger volume of the phase space. And indeed, that was confirmed by several groups of researchers using n-body simulations of merging galaxies. What they have found is that indeed, if they follow the evolution of a binary in a merger simulation, it does not stall, it keeps evolving, keeps shrinking, and eventually goes all the way to coalescence. And the control sample of galaxies which were intentionally created to be spherically symmetric does not display this characteristic. So there is a clear indication that the merger drives asymmetry, and this leads to a very efficient mixing of stars in the galactic center, mixing in angular momentum, and the binary keeps evolving. But the pitfall, of course, here is that we do not simulate real galaxies, we simulate n-body systems. And the n-body system that we can simulate is typically does not have as many particles as a real galaxy has stars. And the difference is by many orders of magnitude. Now, if I recall the theory of two-body relaxation, it is driven by the granularity of the potential, or the granularity of the distribution of stars. So if we simulate the same galaxy not with 10 to 10 stars, but with 10 to 6 particles, of course, each particle has a much larger mass. So the two-body relaxation is greatly enhanced in this case. And in fact, the relaxation rate, the relaxation time scales, is proportional to the number of particles in the simulation, whereas the collision-less effects that I described on the previous slide, this precession of orbits or the change in angular momentum in a smooth potential, that thing is independent of n. So we have clearly here a problem if our collisional effects are much stronger than collisionless effects, then we cannot reliably simulate it in a body simulation. So in order to deal with that, I developed a method which greatly suppresses the two-body relaxation. I'm not going into the details here, just wanted to stress that this is another method which was specifically targeting the evolution of binary supermassive black holes in galaxies. It is still based on particles, but the particles, it's not a direct n-body simulation. The particles move in a smooth potential, so the two-body relaxation is greatly suppressed, and the interaction of stars with the binary is followed as a sequence of three-body scattering processes. So I can pretend that each interaction occurs independently, and then compute the changes of binary parameters as a result of each interaction. And I can also add a desired amount of relaxation to this method. So I can mimic a collisionless galaxy by setting the relaxation rate to 0, or I can mimic a standard n-body simulation by setting the relaxation rate to some reasonable value in order to test it against direct n-body simulations. So using this method, I have found quite an interesting result, I would say. So you would expect that indeed in the non-spherical systems, the binary would not stall, it would keep evolving because there are torques from these large-scale asymmetries of the potential which change the angular momentum of stars. But the interesting thing is that this is not the whole story, because you still need to throw enough stars into the binary, so that into the orbit of the binary, so that they can keep evolving. Basically, the order of magnitude estimate is that to shrink a binary by a factor of 2, it needs to interact with the number of stars equal to the mass of the binary, because they would be ejected with the typical velocity of the binary, so the velocity would decrease, the separation would decrease by a factor of 2. You would need to eject the same mass. And it turns out that this is only possible in non-axisymmetric systems. So spherical systems, of course, would not be able to do that because the reservoir of stars is so small. But even in axisymmetric systems, it's not it's not enough, because the volume of this extended loss cone is still not large enough. So you need some sort of perturbations from axisymmetry, which is quite easy to arrange because in real galaxies they're also not perfectly axisymmetric. There are some residual torques from. Imagine if a galaxy merger occurs in some way that it occurs in a certain plane, but within this plane there are still some asymmetries of the distribution of matter, which create these non-axisymmetric torques. What I show here is the rate of the hardening rate of a binary, not as a function of time, but as a function of the separation of the binary. Just to demonstrate that in the spherical case, the red lines, you slow down, and you slow down basically to 0. So you only can shrink by a factor of, say, 3 or 4 before it stops down entirely. In the axisymmetric case, this is the green line. You also keep slowing down, and eventually it does not stall right there, but it still stalls at only a factor of 10 between the initial and the final separation. Whereas, as I told you, you need to shrink by a factor of 100. So it's only in the triaxial case that you can keep evolving, although the rate of evolution decreases with time, but still it is sufficient for this evolution to lead to the merger within, say, 1 gigayear for typical parameters of the galaxy. So I would say that these conclusion from these studies is that the final parsec problem is indeed not a problem at all. It is solved by assuming more realistic model for the galaxy evolution. I should also mention that this evolution was driven entirely by interaction with stars. But if the galaxy also contains gas, then of course there are also the gas which forms a circumbinary disk. It can also torque the binary so that the evolution occurs faster. Although this is also not so straightforward, because like in protoplanetary disks, the binary, the secondary black hole on orbit around the primary black hole, it opens a gap inside this gaseous disk. So the evolution is determined by the flow of gas through this gap, much like the planetary migration in protoplanetary disks. But I'm not going into the detail there because I'm not an expert on gas evolution. I just wanted to mention that that alone is also not able to shrink it very, very rapidly. Typically, the time scale for this gas evolution is also for the 100 million years or so. So you would expect that the binary typically evolves on a time scale of 1 gigayear. Now, what happens when it shrinks to a very small separation, when the gravitational wave emission really becomes important? Here I just show one formula to stress that the time scale for gravitational wave emission is proportional to the separation in the 4th power. So if you shrink by a factor of 2, it accelerates by a factor of 16. So basically the final stages are occurring faster and faster. It also depends quite considerably on the eccentricity. Here you see this factor here is 1 minus eccentricity squared to large power. So very eccentric binaries can shrink about 10 times faster than almost circular binaries. And what happens in the later stage, of course, the binary spirals in, and it emits a gravitational wave signal which becomes stronger and stronger and stronger, and then whoop, and then it coalesces. So this is what we have witnessed a few months ago in application to stellar binaries. Those ones, I remind you that they were only 30 solar masses each, whereas here we speak about black holes of 10 to 6, 10 to 8, or even more solar masses. But the process occurs in absolutely the same way because the gravity is scale-free, more or less. It's only the time scale that changes here. So whereas well, here the time scale is given in some weird units, which are not the numerical units, but in principle, you could easily estimate the time scale, which is the light travel time for over the range of the light travel time between the binary, between the components of the binary, which is typically for stellar mass binaries it's milliseconds, but for supermassive black holes these could be hours or even more. And of course the hope is that we will be eventually able to observe it using gravitational wave telescopes. Once again, since the time scale are in an entirely different range from the stellar mass binaries, we cannot do it with LIGO, because LIGO can see events on the time scale of hundreds hertz, whereas here we speak about time scales of millihertz. But these events can be seen with a space-based telescope, which has been under planning since many years ago, and in 2011, the first prototype was actually cancelled by the American Senate, but Europeans took it up and they now proposed a slightly modified version of LISA, which is called the ELISA, extended LISA or evolved LISA, yes. LISA stands for Laser Interferometry Space Antenna. So the concept is that it would be a similar structure with 2 or 3 arms of interferometers flying in the space with the arm separation of between 1 million and 5 million kilometers, depending on the details of the design. So it would be put somewhere on Earth's trailing orbit, not even in the Lagrangian point, but somewhere in the far space, and it would detect, since the separation between the detectors is so much larger, it would be also sensitive in much lower range of frequencies. And you see that the typical signal from a binary emerging at a cosmic distance of 3 gigaparsec is way, way above the noise threshold. So we will be able to see these events basically up to the end of the universe, the edge of the universe. So this is a hope that probably this thing could fly in 15 maybe years. I think it's scheduled at present to be launched. Well, not scheduled to be launched, but the idea is that it would be developed in 30s. So the hope is that we will be able to probe directly the evolution of supermassive black holes in a similar way that we now start to probe the evolution of stellar mass black holes using an entirely different means. That is still not the whole story, because when the binary merges, coalesces, it does not do it precisely symmetrically. Basically, there is the emission of gravitational waves. It occurs with some asymmetries. So if it depends very much on the mass ratio between the components, the orientation of the orbital plane versus the orientation of spins, and so on. But the end result is that in one direction you emit more than in the other direction, so you have a recoil velocity. And typically this recoil velocity is of order between a few tens and to a few hundreds kilometers per second. For some specially arranged orientations, it could reach even a few thousand kilometers per second, which is quite a large number. It could be larger than the escape velocity from the galaxy. So you could imagine this huge black hole is just flying out of the galaxy and traveling somewhere in the intergalactic medium. This is, of course, very rare. What is more likely is that it gets ejected from the galactic nucleus, but then at the end it sinks down to the galactic nucleus once again because of dynamical friction. And that process can also take hundreds of million years or even a giga-year. And during this process, first of all, if the black hole has an accretion disk around it, then you would be able to observe something which is off-centered. You see a galaxy and you see some kind of jet or X-ray source which is not in the center of the galaxy. So the hope is to find these recoiling black holes by doing these very precise observations. Another possibility is that when it gets ejected, it can still carry with it a very dense cluster of stars, which might sound quite strange in the view of all stars being ejected before, but in fact, believe me, that more detailed calculations show that it may carry away a very thing which looks very much like a star cluster with the size of only a few parsec, but the velocity dispersion of a few hundred kilometers per second. So it cannot be, of course, a global cluster. It must be something else. Unfortunately, these objects, I think it's hard to observe them unless they occur in one of the nearby galaxies. But off-centered black holes, yes. This is different from, let's say, a slingshot effect? This is not a slingshot effect. Slingshot effect was what I described at the very beginning of my talk, where you have two black holes and the third star coming in and being ejected. Yes. I forgot to mention that this is called slingshot effect indeed. But this is a recoil effect from the emission of gravitational waves. Okay. So this during the merger, during the coalescence of the which is very rapid, we still can hope to observe some electromagnetic signature of this process in addition to gravitational wave signature. Because if the binary was embedded in accretion disk, then of course it evolves very rapidly. It induces a lot of perturbation in the accretion disk, and the hope is that by observing, I'm not sure how that is expected to work, because these timescales are, well, these timescales are quite long compared to what we have in the stellar mass black holes. So remember, using for this LIGO event, there was a hint that it might have been followed by gamma ray transient or X-ray transient. I forgot what was it. But I think it was not very robust. In any case, this transient would have occurred on a very, very short time interval from the emission of the gravitational wave itself. But here we have a much longer time scale. So in principle, if you detect something which looks like a gravitational wave transient, if you can determine the location on sky, then we might be able to point out the telescopes there and see this electromagnetic counterpart. But again, this is still far in the future. So to summarize the evolutionary stages and possible observable signatures, now I'm moving slowly towards the observable signatures. There are many of them at different scales. So starting with the black hole still not having formed a binary, when there are just two black holes in two galaxies in the process of merging. Both of them could be quasars, so you can see some kind of binary quasar. Then when it gets closer and closer, if it is embedded in an accretion disk, then yes, you might see some periodic perturbations to the luminosity induced by the second black hole orbiting the primary black hole and penetrating its accretion disk once in a while. Then during the merger itself, we would see some gravitational wave or electromagnetic transient. And then when it gets recoiled, then we can detect off-centered quasars and these hypercompact stellar systems, and also the depletion of density profile in the galactic center, the formation of galactic cores. So this is all very nice, but do we actually have any evidence for binary black holes? And the evidence is quite scarce. Basically, there are only a few cases where we see something that could be interpreted as two black holes in a single galaxy. This was maybe one of the first, probably the first one, where you see two jets, radio jets, and the points here, this one and this one, is marks the center of the galaxy, of corresponding galaxy. So you see there are two jets, two black holes. But the thing is that the separation between the two components is 7 kiloparsec. And if you remember what I said before, the binary forms at separation of maybe few tenths of parsec. So this is still not a binary. It's still on the way towards forming a binary. Now, this thing is more recent. This is two hot spots in the X-ray observations of some galaxy. Again, here the separation is of order 1 kiloparsec, so this is still not a binary. The only more or less robust case that we see a real binary is here. This is a radio observation which show two sources with the interferometric observation, which show the two sources project a separation of only 7 parsec. So this might be really the only case that we can be sure that this is a binary, although again it depends on how do you interpret these observations. There is another way of getting indirect evidence. For example, in this very famous quasar OJ287, which has been observed for many decades. You don't see here, but it actually, the observation started back there in the I don't know, 1950s or so, and the light curve has been followed for many decades, and it exhibits periodic or quasi-periodic variations in the luminosity, which has been interpreted as a signature of the secondary black hole perturbing the accretion disk about the first black hole. Even the accuracy of this data is such that people were able to work out some relativistic corrections and predict the time scale for the next spike, and they were correct within a few weeks maybe. So this looks quite an interesting candidate. Another possibility of detecting these things would be on a more statistical sense, would be to follow the periodic shifts in spectra of quasars. So if there is a narrow line and broad line component, and if you see that there is a systematic shift in velocity between those two, which is not constant but which also evolves with time in a periodic way, then you could think that there is one black hole and another black hole which orbit each other. Each one has its accretion disk, or maybe one of them has an accretion disk, and there is the broad line component following this accretion disk, and there is a narrow line component further out. So there would be periodic shifts in the velocity space. So there has been several monitoring programs which aim at finding binary black holes in this way. So there is one of the candidates. And this is all of the pieces of evidence that we have by now. So the question is whether these guys exist in nature or not. They probably should exist. They probably should evolve on time scale of gigayears. And the interaction with stars is the crucial part of the evolution. And in reality, we expect that there is no final parsec problem, so they should merge within a reasonable time. Observational evidence for binary black holes is quite scarce, but that may be reflecting the fact that it's really hard to observe them, because if they are so close, how do we distinguish between the binary and the single black hole if only one of them is shining? So I leave you with this conclusion. I think the binary black holes exist and they are fascinating objects to study, but we'll see. The future would show eventually if we do detect them via gravitational wave observation, that would be a smoking gun. But we only have to wait for another 2 decades. Thank you.
Hi. You mentioned the possible effects of gas in these binary mergers. I'm wondering what could be also the role of dark matter. You know, there is a kind of spike of dark matter in the centers. So what could be the role in the process, dynamical process you mentioned, and also the possible signatures, observational signatures, because, for example, from annihilation of dark matter, and could be enhanced by this process. So
thanks. That's an interesting thing, but I believe that it might be subdominant to the stellar interaction. For the following reason, the dark matter is also a collisionless medium, so it would evolve in the same way as stars do. It would experience also this three-body interaction between a single particle and the two black holes. So it would act in the same way. Okay. So I expect that even if there were some sort of spike of dark matter around each black hole, then it might be destroyed at the early stages, along with the stellar spike. I don't think that that has been studied in much detail, but my guess is that if it would be destroyed, so it would form a core, so you don't expect that much of annihilation signal. And in terms of dynamics, presumably dark matter is subdominant to stellar component of the star in the galactic in the center of a galaxy. So it would not add much to the dynamics. But it could be at the level of the gas. Yes, but the gas is a gas acts differently because it has friction. It is not just ejected; it can extract much more angular momentum than the stars can. Basically, for the gas, you only need to have a small fraction of the mass of the black hole being in a gas, and that would still be enough to drive it towards coalescence on a reasonably short time scale, because the angular momentum of the gas is so much larger than the angular momentum of the black hole.
I want to make a comment on the fact that I do believe that there are more cases apart from the great OJ287 that have been found by this photometric method. In the first place, in the case of OJ287, not only the spike has been predicted, but also, at least in the model by Valtonen et al., the secondary spike of the passage of the secondary through the disk. Anyway, there is, for example, 3C66A. It's another blazar that has been shown to have periodicity, and a few others. I agree with you that this is very difficult, doable, but it involves a tremendous effort of observing times in coordinated telescopes all over the world, etc. But I think it's an efficient thing that can be done. Unfortunately, small telescopes are closing all over the world. And this is basically the kind of telescopes that are used to do this work, because you cannot get tons of nights in large telescopes.
Yes, there might be other cases that I just did not show here. The thing is that this is still an indirect method. So if you see some periodicity, you can ascribe it to the black hole binary. You can ascribe it to some blobs in the accretion disk which also move in a quasi-periodic way. So there might be other interpretations. Yes.
Okay, coming back to the gas point, when you have galaxy mergers, so you have gas inflows to the center. At least for the dark matter halos, that tends to make more oblate, axisymmetric. I don't know for the stellar remnant, but do you think this might make weak the solution for the final parsec problem, or maybe make a preference to the circumbinary disk scenario? And do you think there is a way to diagnostic which scenario is making the coalescence, the stellar one or the other one, or maybe they combined?
I think they, in any case, you do have stars there, so the stars would be interacting with the binary. The gas, if there is plenty of gas, then most certainly this is the main driving force behind the evolution. So you would have something like this first stage would be still driven by the stars, this initial hardening. But then instead of this long loss cone evolution, it would decline much more rapidly here. It would still form a core in the stellar distribution because that forms on the early stage, but then eventually you don't have this long bottleneck. The fact that the gas tends to make the system more close to axisymmetry, I think it shouldn't matter that much, because in my experiments, I've seen that even a small departure from axisymmetry is already enough. It changes qualitatively the nature of orbits, because basically in the perfect axisymmetric case, you have another isolating integral of motion. So you can change the angular momentum, but it can never get below the conserved component of angular momentum along the symmetry axis. So getting back here to the loss cone. Sorry. Yes, so in perfectly axisymmetric case, you have variations, but you are always bounded from below by the conserved component of angular momentum. Where even in a weakly triaxial case, you can get all the way down to 0. So this is a qualitative change which is driven even by small perturbations in the away from axisymmetry. So I think in most realistic cases, any small perturbation is enough for this process to be effective. The time scale might be slightly longer, of course, if you have smaller perturbation, but it depends on it quite weakly.
That may affect the abundance of these electromagnetic counterparts.
Yes, yes, yes. One thing that I forgot to mention is that if the evolution really takes that long, like a billion years is a long time, and you could think that there could be another third galaxy coming in during this time. So if you bring a third black hole into it would be also scattered away, but now that the black hole is much more massive, it would be able to shrink the binary by a much larger factor. So the triple black holes are another exciting possibility of dynamical interactions, which may, it has been studied, but again, observational evidence for triple black holes is non-existent.
So I have a question and a comment. First, the comment about the observational evidence. Last year, there was some claim about a tidal disruption flare that was interrupted like periodically. It's very weak, but they say that it might be a TDE from a binary system.
Yeah, that was an interesting paper. I remember it. The time scale of variation would be it would be a fraction of a year.
A couple of months.
Yes, a couple of months. So the thing is that if it is this, it would be a very interesting, but very thrilling, but quite unlikely possibility, because most of the time here, most of this evolution takes place at this long stage where the orbital period is much, much longer than 1 year. So you would be able only to catch it when you are at the late stage of evolution, which take very small fraction of time. So this is interesting, but yeah, I don't know how realistic is that, or maybe we are just lucky.
A little bit weak, yes, I agree. And then the question, in the initial phase, when the binary is hardening because of this free body interaction, why is it that it never happens that a star, say, instead of contributing to the shrinking, separates the binary? Say it gets plunged, it plunges into one of the binaries or something like that. Why is it always in one direction?
Now, there could be, I think there are two effects here. First, that a star can indeed be just captured by one of the components. This is a subdominant process, which nevertheless is interesting because that has been studied in terms of rates of tidal disruption of stars. And what people find is that on this early stage, because there are just stars are reshuffled in a very vigorous way, we have a spike in the tidal disruption rates as well. There was another paper I remember that was suggesting that you may have even one star per several years being disrupted in the galaxy. So if you see repeated flares, tidal disruption flares from the same galaxy, that might be another indication of this stage. But again, the weak point is that this only takes very short interval of time. So it's here, I think it's in mega years. So basically, it's just a few mega years out of this giga year evolution. So it would be very likely to see this star being disrupted twice by the same binary. But the second point is that why an incoming star is always ejected with a higher velocity and not with a lower velocity. And this is this has something to do with the fact that the binary is hard, because a typical incoming velocity of star is of order the velocity dispersion of stars in the galactic nucleus, let's say 100 kilometers per second. But the velocity with which it is ejected is of order the orbital velocity of the binary. So if this is the binary velocity is larger than the velocity dispersion, this is the definition of binary being hard. Then almost always it is ejected with a surplus of energy. And if not, you see that it has interacted once, it's ejected, but then it returns back because it did not have enough energy to escape. So it's kind of this is like this casino paradox. When you when you play roulette, you say or I don't know, you play something that you can win or lose. So you put $1 there, you lose. Okay, you put $2. So if you win, then you get back your $1 and you win another one. If you lose again, you put even more. So you double your stake every time. And in the end, if you play long enough, you will always win, right? So why that? Why nobody gets rich using this process? The thing is that if the star has interacted once and it lost, then it will come again, and eventually it would win.
So my question, I think, is at the outreach level. You mentioned one of the effects of the gravitational wave emission, the recoil of the merger.
Mm-hmm.
But this huge amount of energy released during the merger in gravitational waves
Mm-hmm.
could have some effects on the galaxy, on the nucleus of the galaxies and disordering.
Yes, there could be an effect. The thing is that, yes, energy is released in the form of gravitational waves, which are still very big. They are strong close to the black hole, but then further out they have an amplitude of 10 to minus whatever. So they do not perturb the galaxy that much. But what can happen is that if you suddenly take this recoiling black hole, which has a velocity of a very high velocity, you basically suddenly take it out of the galaxy center. So that would respond by flattening of the density profile of stars, because now you have lost some of the gravitating some of the gravitational potential. So that might have some effect on that.
Okay, if there are no more questions, thanks again to Eugene for a nice talk.